I just want to give you maybe a simpler example that was actually connected to spin transport in one-dimensional systems, where we're trying to set up a one-dimensional Heisenberg chain, and we want to learn about spin transport, the nature of spin transport in the system. So we can set up, for example, like a domain wall that you can see here, all the spins up here, all the spins down on the right-hand side at time 0, and then we let this domain wall, magnetic domain wall, evolve as a function of time, and you can see how atom by atom they're propagating from one side of the domain wall into the other one, and then by repeating the experiment thousands of times, we can measure again the full counting statistics of this experiment. Now, why was this experiment for the Heisenberg model? Because people had been predicting there's a new form of quantum transport occurring in this system, a new way of a new universal law that maybe would be governed by what people call the so-called Carter-Parisi-Jean equation. So this is actually an equation, a very famous equation from statistical physics that tells us something about the growth of surface when you drop particles from above onto a surface, and it tells us something about how does this surface grow as a function of time. And here you can see just a picture of how this would look like in an experiment. It's governed by this nonlinear stochastic partial differential equation, and people actually conjectured that such a nonlinear partial differential equation could maybe also describe the spin transport occurring in our Heisenberg experiments. That's really what we strive for in physics. We want to find universal laws. We, of course, can calculate the full Hamiltonian evolution, but at the end of the day, as a physicist, I want to find a simple formula. I want to find universal concepts that underlie all this quantum transport. So being able to find that, or being able to identify new universality classes of this transport, would actually be a very big thing, a very nice thing to do that. So that motivated us to study that and really measure this full counting statistics in the experiment. And actually we found that actually it looks like there's indeed this Carter-Parisi-Jean universality class at the bottom of this, a new universality class, very special, done to only new, basically from classical physics, that governs the spin transport in these systems. Then actually Google did also the experiment. Also this year, there was a very nice paper from the Google team doing precisely the same thing on the Sycamore quantum processor, setting up this domain wall that you can see here, and then just checking how do the spins move over from the domain wall into the other part of the magnetized region. And then also measuring the distribution functions. And they could go to measure this a little bit more precise than we could, not to as long times as we could, but they showed that, well, it looks like maybe there's even a new universality class that we hadn't heard about before in this system. So I think, this just shows you, by having these powerful tools at hand of measuring the full counting statistics, we can really access quantum transport in completely new ways on these devices. And I think that's a very beautiful and powerful way to study these phenomena. All right, in my last few minutes, I just want to give us an outlook. Where can we head next? And we have the digital quantum computers, the circuit model. We have the analog systems that I told you about before. And we also, I told you that I think each one of them has, depending on your problem, advantages and disadvantages. And maybe for the future, marrying those both worlds will be interesting to get the best of both. So having an analog operation which can take you far out on your NISQ devices, then having digital readout or digital preparation to measure kind of very complex systems. And if we want to do that in our systems, where we have dealing with moving particles, where we have orbital degrees of freedom, we really have to think of a new Bloch sphere that I would just like to make you aware of, that we want to measure and that we can measure now in the experiment. So you're all aware of the Bloch sphere in spins, but here's a little bit different. So imagine we have our lattice system that you have here, and we want to now not only measure the occupation of the different lattice sites, but I also want to measure some things like the kinetic energy or the currents that are flowing between one site and the next site here. How can I do that? And how can I think of that in terms of a Bloch sphere that I have? So the way we think of this is that, if this is the physical system, we can, for measurement purposes, partition it into an array of double wells that you can see here. And this array of double wells is now like a Bloch sphere, where you can basically do sigma x rotations. You have a particle being on the left-hand side, on the right-hand side. These are like the 0 and 1 of your qubit. And you can have tunneling from left to right that corresponds to sigma x rotation. Or if you detune the double well in your orbital degrees of freedom, then you basically are making a sigma z rotation of your orbital qubit. So we can think now of this Bloch sphere picture of the orbital degrees of freedom that we have at hand, where the z-axis, that would be basically just corresponding to density measurements that I told you before. The x-axis would be measuring the kinetic energy in the system, and the y-axis would be corresponding to the current operator of the current flowing between two lattice sites in the system. And we can move around on this Bloch sphere, and by doing suitable rotations on the Bloch sphere, we can measure either of these quantities. And this is, of course, very nice, because then we can not only measure occupations, but we can also measure currents or kinetic energies directly in our quantum simulator. And that gives us access to these phase factors that I alluded to before, that are present in the many-body wave function. Just to show you an example of this, we can, for example, create a situation where we have currents flowing here between these sites and opposite currents flowing in the opposite sites here. And we can measure that in the experiment using this readout scheme, using these double wells that I showed you before. And here's a measurement of these currents, allowing us also to measure, for example, current-current correlators and things like that. And you see this very good agreement with theory. And this, I think, is a significant enhancement for us that allows us to measure now all quantities of this Hamiltonian in the experiments and even higher order correlation functions in this. So in looking a little bit ahead, there's been exciting developments in the field. You've heard about the fantastic work of the tweezer arrays in, for example, Misha Lukin's group. And I think there's this very nice work from Adam Kaufman in Boulder, who's marrying the optical lattices with the optical tweezers. And I think that's going to be a very powerful approach, because the lattices offer a pristine storage environment and the tweezers offer the ability of shuttling these around. And then there's the enticing possibility to also put completely new particles into these lattices and do like really small chemical reactions between individual atoms to form molecules out of them. These molecules can have long-range dipole electric interactions. So this is something, for a physicist, a fantastic playground to work on, so to study with, absolute quantum control, also these chemical reactions in the system. So just on this middle part, let me show you a little bit of finally our progress we're doing here in Munich. Here's a picture of a lattice loaded, a very large lattice. Each individual point here is a single atom. So there are over 10,000 atoms now loaded, individual atoms loaded into this register, into this lattice. And we are now trying to marry this with the tweezers, where we can move atoms around now in the lattices, and showing we can hopefully marriage these large-scale storage devices where we really have a large amount of qubits or atoms in the system, and we can combine that with the beautiful physics of the tweezers, where we can move these things around. And that is, of course, very exciting for the future to be able to develop these techniques. Okay, finally, let me just, for the last few minutes, let me just give really credit to the people in the lab who have been doing the work. And so there's been a fantastic team of PhD, postdocs, and group leaders on that. So on our rubidium quantum gas microscope experiment, Johannes Zeyer is leading that, and David Wade did the fantastic work on the KPZ experiment here. And on the fermion experiment I showed you before, and most of the work on the polaron was actually done by Janis Köpsel. That was his PhD work. And the newest data actually on the large polaron that you've seen that we're going to publish hopefully soon, that's work here of this new team of students. Thomas, C, and Peter are working on that experiment. The CSIM experiment also showed some data on the orbital kind of degrees of freedom. That's work I'm doing together with my colleague Monika Eidelsburger here in Munich. And that was mainly work by Alex Impertro, showing you this new Bloch sphere for orbital degrees of freedom that we are working together with. All right, Zlatko, I'm at the end of the talk. I leave you with this nice picture from Munich, and thanks a lot for all your interest.
One of the very first questions that we skipped over, and you sort of alluded to it or touched on it, is just a better understanding of some of the main advantages and challenges for ion-based systems and these kinds of systems. And now it's incredibly interesting, of course, that lattices are merging now with the tweezers, yes, in a new direction. But maybe if you give folks who are not from these three communities a bit of an overview of how to think about the three?
Okay, so we have, I would say the lattice and the tweezers, they're very naturally connected. That's very close to each other. We're dealing both with neutral atoms. They're both trapped by light fields, either by a focused laser beam, that's the tweezer, or by a lattice, which is the structures I told you about. And you can easily connect them, combine them. And that's very natural. You're just using them for different purposes. The lattices are more, purposeful, I think, for if you want to do, let's say, directly material simulations. If you directly want to do a quantum simulation of your material in a certain lattice structure, the lattices are a very interesting way to go. They're also, in a sense, can allow very large structure sizes. If you think about 3D, we can even think about going to 1 million atoms in 3 dimensions. So scaling that to 3D. It has a lot of potential there. So, and they can act, for example, the lattices could also be good storage registers where you store qubits or atoms and then move them around with the tweezers. So that could be a very nice combination of the two. The ions, again, a completely different platform. We're dealing, charged atoms. We've removed one electron, so they're positively charged. They are trapped in electromagnetic traps, typically Paul traps. These are typically one-dimensional geometries, where you basically most of the time dealing with about 50 ions in such a one-dimensional geometry. Okay, you can also have nice, I think, racetracks like Quantinuum, what they're doing. So that's a little bit the difference there. I would say what's really nice with the neutral atom platform is that it scales very nicely, as you've seen. There's very easy to scale this platform. I think the ion trap is a bit harder, as we'll see. There are a lot of interesting concepts around, but to scale might be harder there.
At what point, this is a question that comes up often in discussions, at what point do you run out of laser power for these systems?
Yeah, that's a good question. We always want the powerful laser, so we have a lot of powerful lasers in the lab. That can become a limit and will become a limit, I think, but not on this 10,000 site scale yet. And I think there's a lot of cool stuff to be done on a 10,000 site scale. So if we want to go to 100,000 or million, then I think we might have to go to 3D. Then I think we'll have going to run into the problems that you mentioned. But on the other hand, it might be just a technical problem. A laser, I mean, we have kilowatts, 10 of kilowatts lasers around. We're just using the 100-watt version, which is dangerous enough, but yeah, I think that might require some more engineering, but it's not completely out of the question. Or we could use cavities to enhance the light fields to make them stronger. So there are a lot of, but I think until this range of 10,000 qubits, there's not a problem.
Okay, excellent. Speaking of numbers, there was a question from Kaylin around what are the largest lattices that you have manipulated to date?
Yeah, so on the Hubbard model systems, I think there were about 3,000-4,000 atom systems. This one that I showed you here, and this one picture, where is it? This one is like over tens of thousands of particles in this lattice.
Great.
So that's the largest one we've imaged, and we're also manipulating atoms with the tweezers in this lattice now.
I think you showed us that you can measure entanglement entropy. Maybe you can remind us how that was performed. Is it possible to measure an entanglement spectrum?
Yes, so entanglement spectrum is also possible. That was recently done, but that was done more in the ion trap, not in the neutral atom community. So far, there's been a nice work in the ion trap community just very recently. So this von Neumann entropy, or the Renyi 2 entropy, actually was measured with basically a many-body Hong-Ou-Mandel experiment. I guess a lot of you will be familiar with the Hong-Ou-Mandel experiments for 2 photons on a beam splitter. And what you can show is if you do that, like this is like you have to initialize your system in 2 identical copies, and then you basically do such a many-body quantum interference like a Hong-Ou-Mandel beam splitter, and then you read out. And from reading out this many-body interference, you can actually reconstruct the Renyi 2 entropy and the purity of the state that you have.